Okay, now let's discuss another algorithm that solves the problem of multi-objective optimization, and the new algorithm will hence be called as the multi-objective evolutionary algorithm, as you would expect. And the added flavor is by decomposition, or in short, MOEA-D, multi-objective evolutionary algorithm by decomposition. Now, we discussed NSGA and it seemed to be doing pretty good. There weren't any specific problems really. The one problem that comes over is we were using primarily two objective functions, the first one being the Pareto rank, and once you have 1, 2, 3, or maybe 4 objective functions, it works brilliant. The moment you increase the number of objective functions, virtually every individual is rank 1 non-dominated. So the more the number of objective functions, the more number of individuals are by default, without doing any optimization, rank 1, and then it's primarily up to the diversity to just increase it up. And sometimes the fitness so the objective spaces can be extremely critical, so there are regions where getting individuals by the kind of mutation and crossover that the genetic algorithm uses is not always easy, it's not always possible, and the NHGA does nothing in that respect. So now we'll be solving a problem in a slightly different way, and the slightly different way is eventually what I need to do. I need to optimize some objectives, F1, F2, and so on. So these are my objectives. Because the problem is multi-objective in nature, let us do a thing which has been done classically for a very long time. So I convert a multi-objective optimization function into a uni-objective optimization function by a weighted addition. And I say that this is a function that will have to be optimized. Let us say this is some g function which has to be optimized. And I'll optimize this function. Now let us see what this thing is really into. The objective space. So let me draw an objective space over here. And this is f1x, this is f2x, and similarly they have other x's possible. A constraint here is that all wi should be greater than 0. A minimization problem cannot become a maximization problem. So if I represent what is gx, it's actually a line like this that passes through the origin. So it's a line that will pass through the origin over here, and this is what's called as gx. And because there's a weight involved, so let it be called as gwx, where w is all these weights which are over here. So the line is called as gwx. And what this value is, f1x plus f2, w1 f1x plus w2 f2x. So let's take any x around over here. So I take this as the x function. So this is the value of gwx over here. So gwx is nothing but the projection of a line, the projection of a point x on a line represented by w1 f1x plus w2 f2x and so on, or it's the projection of a point x on the line whose equation is given by gwx is equal to 0. This can also be represented as any general W dot product with fx, where of course we have seen the definition that fx is f1x, f2x, and so on fmx. So with this understanding, let us construct a objective space again, so that's f1x, f2x, and all the other dimensions, and plot an infinite number of individuals which are non-dominated or the Pareto front. So that's my Pareto front. And let's again draw the line GWX is equal to 0. Now, starting out from anywhere, so that's a line GWX of it is equal to 0, and let's say that this is what I call as the normal of this line. So if I take in any general x, and I move it around in such a way such that this objective function GWX is equal to W1x1 plus W2x2 plus W3x3 plus WMXM is minimized, and I do this thing over here by moving x. So at every point of time I am minimizing this projection. So at every time I'm minimizing this projection. So if I need to minimize it up, let's travel in this direction. Now, is this the optimal value? No, because if I move here, then it further gets optimized. If I move here, it further gets optimized because this projection is reducing. So let's move a little bit more. This projection is reducing. Let's move in a little bit more. This projection is reducing. Let's move in a little bit more. This projection is reducing. If I start moving it further, then this projection starts to increase. So the optimum point which I will get is over here. So let's call it as the X star. I cannot move beyond this thing because the actual motion is happening in the decision space. So I'm actually moving around over here. It's just that I am looking at its effect in the objective space here. So there's no individual which is possible. No individual here gives me these points. Otherwise, this would have become dominated, and the Pareto front would have got further modified. So XR is the one that minimizes, or it is the one that minimizes. So this gives me 1 point on the Pareto front. This gives me 1 point on the Pareto front. And because it gives me 1 point of the Pareto front, I can use many weights like this to get many points on the Pareto front. Now, before I move further, I will be making in one small change. And that small change is, imagine two objective functions. So f1, x1, x2 is equal to x1 minus 5 plus x2 plus 10, and f2 x1 x2 is equal to x1 plus x2 minus 5. So let's take these two objective functions. The utopian point is minimum over all x f1 x comma minimum over all x f2x. So the lowest value of this becomes, when x1 is 5, this becomes 0 plus 10, and the minimum of this one is what is a 0. So now I've got the first function which will never get a value less than 10, and the second one could potentially even go up to a value of 0. So that means my actual Pareto front is not the one that I was drawing. So it's not the one that I was drawing. F2 can go up to 0, but F1 can only go up to 10. And therefore, it really does make a lot of sense to use a modified axis system in order to be closer to the diagram that I was drawing before, which is this and this. So that's my new coordinate axis system. So this is x1 f2x minus 0, and this axis system is f1x minus 10. So now here the vectors will be nice, it'll be good, it'll be a nice shape around over here. Both coordinates will go around 0. So therefore I use the same equation, and the first thing that I do is I modify it up a little bit. So my function is given by gwx is equal to w1 times f1x minus u1, the minimum value that this function can take, plus w2 times f2x minus u2, and let's put it as a star. So that's the optimal value, plus all the way up to wm fmx minus um star. Now, instead of taking one weight, I'll be taking in a lot of weight. So let's say this is the ith weight vector, and let's add ith weight vector over here. So this can be represented by the dot product of wi with capital Fx minus u star, where capital Fx of course is equal to f1x, f2x, and so on, and u star is the utopian point, which is u1 star, u2 star, um star, and of course m is the number of objective functions. So everything will be done in an objective space. So things are done in the decision space, but I always map the solution to an objective space. So my logic is simple. So my logic is absolutely simple, and all that my logic says is that instead of solving a multi-objective optimization problem, which I cannot solve, which is hard, which has issues that I don't like to discuss, which is something that I would like to avoid, which is something that I don't know, solve n single objective optimization problem, which is for which I have a lot of algorithms available, which is what we have discussed a lot, which is where a lot of optimization solvers are existing. So instead of solving a multi-objective optimization problem, I solve n single objective optimization problem, where problem I is given by GWI, where this is the first parameter, which is the weight, x is equal to Wi, the weight vector, which of course is a m cross 1 dimensional weight vector, cross fx, where f is the objective space function, So x is a decision space variable, and f of that is f1x, f2x, f3x. It's objective space, so there's another m plus 1 variable. I take the dot product of both of them, and this is the one. And because I need to consider the utopian point, I subtract the utopian point. So my algorithm is absolutely very simple now. All my algorithm says is that Wi random weight vector, and I solve GWI and that's all that I have to do. I've converted a multi-objective optimization problem into n single objective optimization problem, so that's for all I from 1 to n.